Kia ora whānau, good evening. Thanks for tuning into tonight's webinar. This is the third and final online event of our Seaweek Ngā Kōrero III Series. In each event of this year's series, we focused around exploring one of the 7 ocean literacy principles, with the goal of increasing ocean literacy across Aotearoa New Zealand. Ocean literacy generally means understanding the ocean's influence on us, as well as our influence on the ocean. Tonight, we'll be exploring the third ocean literacy principle, that the ocean is a major influence on weather and climate. Ko Alison Ballance tēnei, I'm your MC. I write nature books, I'm a broadcaster, I love walking on the beach, I think diving and snorkeling are terrific, and generally ain't the sea wonderful. With me virtually, we have 3 amazing guest speakers who will dive into the connections between ocean, weather, climate, and ourselves. I'll introduce them shortly, but first, a karakia to start. Whakamana te maunga, whakamana te wai. Hei mauri o ngā tangata, ngā mea katoa he pai. Homi e, hui e, tai ki e. If we look after the water, from the mountains to the sea, it will look after us. It is our life force. Kia ora. If you've joined us before, welcome back. If this is your first time here, a very big hello. We always like knowing where you are, so please introduce yourselves to us in the chat. If you don't know where the chat icon is, look at the bottom of your screen and you can access the chat via the text bubble icon down there. And that should bring up the chat panel over on the right-hand side of your screen. We're also starting a poll now, or Laura is. She has a few quick questions for you all. Please take part right now. While you're doing that, a bit of background about Seaweek Kaupapa Moana. It's New Zealand's annual national week celebrating the sea, Te Moana, and it's coordinated by the Sir Peter Black Marine Education and Recreation Centre. Seaweek's pinnacle of events occurs annually at the beginning of March, but Seaweek has a year-round mission which is about exciting and inspiring all New Zealanders to strengthen their connection with the sea. So this series is designed to help us all understand the many ways that our daily lives are intertwined with the ocean. This is the final webinar of this series for this year, but do watch any of our previous webinars anytime you like on the Seaweek YouTube channel. We are recording this webinar so you can watch it again, and of course you can share it with others. A huge thanks to our long-time supporters of Seaweek, the New Zealand National Commission for UNESCO, who make this webinar series possible. Right, down to business. Tonight's topic, it's about how the ocean influences our daily weather and the long-term climate. What's changing and how we can respond. Our speakers will help us understand the systems involved and look ahead to the future. We've been seeing quite a lot of news on this topic lately around how weather forecasting is changing on account of warming ocean temperatures, how the Earth is reflecting sunlight differently, and we've just heard about a new investment in climate change resilience research, just to name a few stories that have been in the news. We can't wait to hear from our 3 fantastic speakers tonight to share their perspectives. Let me introduce them. Our first speaker will be Dr. Cliff Law, who's a New Zealand Prime Minister's Science Award-winning biogeochemist. He's at Earth Sciences New Zealand and the University of Otago. Cliff has advised the government on ocean policy and climate change. He's led NIWA's Ocean Climate Interaction Programme, New Zealand's ocean acidification projects, and much more. He will overview the ocean climate system, highlighting how the ocean acts as a buffer against climate change. After Cliff, we'll hear from Dr. Matt Pinkerton, also joining us from Earth Sciences New Zealand. Matt's research combines satellite remote sensing data and ecosystem modelling to understand how environmental shifts alter marine ecosystems. He's going to share the latest information on what's changing in our ocean and what that may mean for our future. Our final speaker will be Isaac Moranga, who is the Special Advisor Youth for the New Zealand National Commission for UNESCO. He will explore the human connection between the ocean, weather and climate, how Indigenous and youth voices offer vital perspectives on kaitiakitanga and environmental stewardship, and the importance of weaving these perspectives into national and global decision-making. After all of the speakers have presented, I'll ask them your questions. You can send us your questions at any time using the Q&A function, which you will also find at the bottom of your screen. So let's get the show on the road. We're going to start now with Dr. Cliff Law, and we're going to explore the ocean climate system and what the ocean is doing for us. Over to you, Cliff.
Kia ora, and thank you, Alison. And yes, tēnā koutou katoa. I'm going to be talking today about what the oceans have ever done for us, which for those of the older generation probably know is a spin on an expression from a Monty Python film. But I'm going to use this image first of all just to look at our planet Earth, or planet ocean as it really should be called, because we have to remember that 71% of the surface of our planet is ocean, and so clearly it plays a big role in determining our climate. So what I'm going to talk to you about today is not so much about how the weather is affected, but actually how the ocean is a major control of our climate through the carbon dioxide it removes from the atmosphere and also the heat it removes. And I'm going to show you what the mechanisms are for this, but then I'm going to give you some of the information and show what the implications of this are. So the first thing to answer my question, what's the ocean ever done for us? Well, the ocean has kept us safe because the ocean has actually removed 25 to 31% of our CO2 emissions from the atmosphere. Now, I'm sure you're aware, you don't need to see this figure on the left-hand side of your screen to know that carbon dioxide is the main gas that is driving climate change, and that has been going up in our atmosphere monotonically, as shown by this time series in this plot in the left-hand side. But the important thing is that only 50% of this CO2 that we're releasing is remaining in the atmosphere, because the other 50% is being taken up by the land and the ocean. And you can see that in the right-hand figure. And I've shown the ocean indicated there within that blue wedge going up. That's the proportion. So that's that 25 to 31% of the CO2 emissions that our oceans removed. And so you can see if it wasn't for the ocean and land, the atmospheric CO2 would be a lot higher and we would be in a lot more trouble. So let's have a look at some of the reasons why the carbon cycle is so important. So this is I won't go into a lot of details about the carbon cycle. This is just a graphic to show you about the movement of the carbon from the atmosphere to the ocean. And of course it involves also transfer of that carbon to the sediment. Now, this carbon moves around in the ocean on varying time scales from minutes to absolutely millennia, and it occurs on various spatial scales as well. And the carbon is changed from the form of a gas in carbon dioxide to dissolved forms to solid phase and particulate, and it can be inorganic or organic. So it's a difficult cycle to follow around, particularly as it involves biological, physical and chemical pathways. So rather than go into lots of detail, the two big things I want you to take from this is that, first of all, you notice there's big pools of carbon here. These numbers are gigatons of carbon. So that's a billion tons of carbon we're talking about, each of these numbers per year. And you can see that the ocean is both a source of carbon dioxide to the atmosphere and a sink. You can see that in those 290 numbers here. But the net difference, what we're interested in is the actual net uptake is really very small. That's just that 2 gigatons a year. So it's very small compared to the major fluxes. So it's a very difficult number to measure. But the other important thing to take home from this is this big number down in the corner. The deep ocean holds a lot of carbon. Compared this to the atmosphere, is about 800, the deep ocean, 37,000 gigatons of carbon. So there's a huge amount of the carbon. It's the largest carbon reservoir in the Earth system. Okay, so some simple facts. So how does the CO2 get into the ocean? Well, it's clearly just exchanged at the surface, not just CO2, but many other gases as well. it diffuses across, but actually that transfer is enhanced by winds and waves. We've all seen it at the ocean when we've been out surfing or swimming, where the gas bubbles are forced down into the ocean, and that accelerates the transfer of gas into the surface ocean. But if you look at this figure on the bottom left, you will see this is a profile of dissolved carbon dioxide in the ocean. And you can see as you move down from the surface to the deep water, you can see that that CO2 is increasing with depth. So what's the reason for this? If it's going in at the surface, why is it higher at depth? So that's what I want to tell you a bit about. It's about these transfer processes that move the CO2 from the surface water into the deep ocean. And these involve a couple of what I call pumps, which I'm going to describe to you in a minute. But the important thing for us is that by moving this carbon away into the deep ocean, that locks it away from the atmosphere for a long period of time, which is important when we're thinking about climate change. So first of all, let me introduce the thermohaline circulation of the ocean. So this sounds complicated, but it's got the simple name of the ocean conveyor belt. So this is the major movement of water around our planet through the ocean, and it's driven by the density of the water. So it's called thermohaline circulation because thermo means temperature and haline means salt. And so it's dependent upon the temperature and salinity of the water. So what happens if you look at this here, when water moves north, and so it moves up, let's say into the Atlantic, towards the Antarctic, it's cooled by the winds, and so its temperature lowers, but it also becomes denser because of the salt that's rejected by ice forming. So you get this dense water forming up in Antarctica, and it's denser than the surrounding water, so it sinks, and that kicks off this whole conveyor belt, this movement of water around our planet. You can see it following the blue line here as it moves down through the Atlantic and around Antarctica, and some of it moves into the Indian Ocean, where the wind-driven upwelling brings it back to the surface, and it warms and starts returning on this journey. Now, some actually goes the whole way to the Pacific, where it upwells, again due to wind-driven events, and that brings this to the surface and takes it back to the start. So this overturning lasts about 1,000 years, and clearly it's responsible for actually driving and moving everything that's dissolved in the water around our planet for the mixing and the ultimate control of climate. So let me show you what that means in terms of CO2. This is just a section across the Atlantic. So we're looking at depth here. So there's the surface, there's the deep. This is the southern hemisphere. This is the northern hemisphere. And what you're looking at is the color of the CO2, but this is the CO2 we've emitted. Okay, so it's based on everything that's gone from the atmosphere that has originated from us burning fossil fuels. And as you'd expect, it's highest in the surface water, but you can see that in the polar regions where this cold, dense water is formed, you can see it's pushing down to depths. It's getting actually down to about 2,500, 3,000 meters. So you can see this ocean conveyor belt in action, transferring carbon dioxide from the surface down to depth in the ocean. And this doesn't just go for CO2, it goes for oxygen, nutrients, and heat and salt. So it's very important control of our climate. Now that's what's called the solubility pump, but now we go to the biological pump, and this is based around the phytoplanktons, or I've called them the microbial heroes of the ocean. These are the microscopic algae that exist there's millions of them in a litre of seawater, and they photosynthesize, and by doing that they remove CO2 and they convert it to organic carbon within their cells. So they're responsible for about 50% of global primary production, and that provides by production of oxygen, it produces about 50% of the oxygen production on the planet. And we also call them the grass of the ocean because they're the base of the food web. So the phytoplankton are here taking up the carbon dioxide, and a lot of the phytoplankton is just grazed by zooplankton and that passes up through the food web, through other organisms to fish, birds and mammals. So a lot of this carbon is just simply being circulated through this. It's coming into the surface, it's going out as respiration. But a small part of this is actually being transferred in the deep to the deep ocean by dying and sinking phytoplankton in the form of this marine snow, as we call it. There's a picture of it there. So this is just the dead particles and cells that are sinking down. Now, not much of this phytoplankton makes it to the deep ocean. Less than 10% gets to 100 meters, 1% to about 1,000 meters. Only 0.1 is buried. But this biological pump, as we call it, is still transferring a significant amount of carbon to the deep ocean. So that's all good, but we then come on to think about, I told you about how much dissolved carbon there is in the ocean, and that's because carbon dioxide doesn't just remain as a gas. There's this interesting natural phenomenon called the ocean carbonate buffer system, because when CO2 goes into the ocean naturally, it forms an acid. It combines with water and it forms this acid called carbonic acid, which is very weak. Now, this acid splits up and it forms bicarbonate, but it also adds hydrogen ions to the water. Now, hydrogen ions are what make as a measure of acidity. So as the hydrogen ions increase, the pH would go down. But the ocean's got this natural buffer system in that it has carbonate, and the carbonate reacts with the hydrogen ions and forms more bicarbonate. And so this carbonate buffers any change in the ocean. And that's been the way for millennia now, in terms of this natural system with the supply of carbonate from rock weathering and sediments matching this input of carbon dioxide and acidity. But we're changing all this now. And this is where I come to talk about ocean acidification, because we have been putting much too much CO2 into the atmosphere. And so what this is meaning is that there's more dissolved carbon dioxide in the surface ocean. And so what that means is that through this process, there's more generation of acidity in the ocean. So the hydrogen ions go up and the pH of the ocean therefore goes down. Now, the natural system would try and buffer this, but unfortunately, we're putting so much carbon dioxide in at such a rate into the surface ocean atmosphere that the natural carbonate supply cannot keep up. And so the dissolved carbonate is dropping. So simply put, I know that was a lot to follow. This is basically summarized in this graph here, that as the carbon dioxide goes up in the blue line, the carbonate will drop and the pH will also drop. And it's these combined changes, more carbon dioxide, less carbonate, lower pH, is what we call acidification. Now, this isn't just something of the future. This is something that's happening now. And so this is some really nice data to show what's happening in New Zealand waters. So the red line that you see there is the measurement of atmospheric carbon dioxide that's made in Wellington, and that's been going on since the early 90s, and you can see the CO2 going up in the atmosphere. And that's being matched by the carbon dioxide that's dissolved in the surface ocean off Otago at our monitoring station. But you can also see that not only are these two matching each other, atmospheric CO2 going up, surface water CO2 going up, but the corresponding pH is dropping. So we've got real cause and effect there to show that CO2 is driving a pH decrease in our ocean. And so it's acidifying at a rate of about 8.6% over the 22 years of this time series we've measured. So really what I'm showing you is that acidification is happening here and now, and it's happening in our waters. Now, if we look at much longer time scales, and I mean much longer, so if we look at going back the last 25 million years, we can get estimates of how the pH of the ocean has been. And you can see that as we come forward in time for 25 million years, it's been fairly stable until recently. So in the last 250 years, because of all the fossil fuels we've been burning, that pH has dropped by about 0.1, which doesn't sound like much, but that's a 30% increase in the acidity. And then what's projected for the future, if we carry on at our rate of CO2 emissions, that will drop by a further 0.35, so down this vertical line. So that's 150% increase is projected in the acidity of the ocean. So as you can see on geological timescales, this is an unprecedented rate of change in the pH of the ocean, 100 times faster than at any time over the last 25 million years. So that spells problems for the things that live in the ocean. So I could spend all night talking to you about the impacts of acidification in the ocean, but this is just a quick summary to show you that it's not all doom and gloom. There may be winners, things that photosynthesize like phytoplankton, seaweeds and seagrass might benefit for the increase in CO2, but it's these organisms that rely on the carbonate in the water to grow their shells and skeletons like corals and kinna and paua and mussels, which might be the losers. And of course, that's going to affect the habitat, the biodiversity, the food web, and the services that we take from the ocean. Now, that's a brief bit about CO2, but the other side of the coin is that the ocean has also been helping us because it's been absorbing all the heat. So this is a simple plot here that shows you the amount of extra heat that's been retained in our Earth system that's resulted from climate change. And you can see that if you look at the brown, there's a small amount in the land, the white, there's a small amount in the ice, but the dark blue is the ocean and the light blue is the upper ocean. And you can see that the ocean is doing more than its fair share here. It's actually absorbed 91% of the extra heat that's going into our atmosphere from greenhouse gases. And this varies by region, but as you can see, if you look at this plot down here, some areas are cooling around the world, like there's actually cooler waters in the blue, but we, New Zealand, are in an area which is warming quite dramatically. So this warming is going to cause changes like melting of glaciers, ice sheets, and sea level rise, but it's also going to affect things like oxygen availability in the ocean, because oxygen becomes less soluble as the water becomes warmer, and you get increased activity and respiration of organisms, and also slower water formation. So all those three things are combined to reduce the supply of ocean to the oxygen, which is going to impact biodiversity and affect organisms, particularly more active species. And a final summary about what this also means. So we're looking in the future at a warmer, fresher, more acidic and less oxic ocean. And if we think about the surface, particularly where those important phytoplankton live that are driving the carbon removal, that surface layer is going to get warmer and shallower with less nutrients coming up into it. So the future for the carbon dioxide, for the phytoplankton remains uncertain. And Matt will be talking more about that in his presentation that follows. So to summarize very briefly, the impacts of climate change will be far worse if the ocean wasn't taking up carbon dioxide and heat from the atmosphere. Unfortunately, the consequence of this is that this is resulting in ocean warming, acidification, and hypoxia or low oxygen, with serious impacts on ecosystems. Now, of course, mitigation and adaptation are possible, but the key solution to preventing all this is carbon emissions reductions. Thank you very much.
Kia ora, thank you, Cliff. So much to think about. Gosh, the ocean and the atmosphere and the way they interact is so dynamic and so complex. I wrote myself a couple of notes, which was that next time any of us are watching the waves at the beach, we should be thinking about how carbon dioxide is moving between the air and the sea, how the seawater is moving around the world on that global conveyor belt, and how phytoplankton are microbial heroes, especially when they die. That and so much more. Thanks, Cliff. Now, if you have any questions, please ask them in the question and answer, and we will come back to them after everyone has presented. But now we're going to hear from our next presenter, Dr. Matt Pinkerton. Matt will share what's happening now with environmental change in our ocean and what's in store for the future of our marine systems. Over to you, Matt.
Thank you, Alison. Hopefully you can hear me.
Yes, right. You're coming through loud and clear.
That's great. And you can see my screen?
Yes, I can see your screen.
Great. Okay, I'll crack on. It's been great finding out where everyone's coming from around New Zealand. Shout out to the comment from Lake Taupo. Happy to talk about that offline. That's really interesting. Kinloch's one of my favourite places in New Zealand. So my name is Matt Pinkerton. I'm from Earth Sciences New Zealand in Wellington. There'll be a prize at the end if anyone can identify these fish. Actually, you know, since we've been recorded, there's disclaimer, there's no prize, but you get kudos if you can identify these fish, and they're not whitebait, but they're a species that's likely to get wiped out by climate change in the long run. So see if anyone can identify those. So I'm going to talk about what's been happening in our marine ecosystems and what's likely to happen in the future. So the idea of this is to describe the past, understand the present, and use that understanding and that description of what's happened in the past to predict what's going to happen in the future, so that we can hopefully avoid the worst of what's coming. So starting off with what's happened in the past, most of what I'm going to talk about is around satellite data. So we are really in the age of satellite observation. So when I started my PhD, which seems like a long time ago, we were just getting the first ocean color satellite launched. And the first satellites that look at temperature of the ocean had only really been launched in the sort of 1980s. So we're not very long into the era of Earth observation, but really it's revolutionized our understanding of the ocean. And really, a lot of that we owe to NASA, and a lot recently as well to the European Space Agency. So we're benefiting from this great investment that's happened in terms of Earth observation. And there's all kinds of satellites. People that have looked up at the night sky in a dark area, you can see the satellites going over, and we're getting this huge amount, this flood of information from the satellites. One of the things that the satellites do is they measure the temperature of the water. So you can look at the infrared radiation coming off the water and work out how warm it is. And from that, we can map out what the average temperatures are, and we can correct for the seasonal variation and look at whether we get these patterns in warming and cooling in the ocean. So this is just some examples. This is 2004, which was a particularly cold year. 2020 was kind of a normal year. 2022 was a warm year. So we can start looking at where is warming, and different parts of the ocean warm in different rates and at different times of the year and in different years. So we're really trying to understand those patterns of warming. We can take the whole EEZ and take a sort of average temperature across that and try and look at how the New Zealand region as a whole has been faring since we got this first satellite data in sort of 1981. So we've got kind of this 40-year, 45-year time series. And what we're seeing here is the red line is the average across the whole world, and the black and the blue are the averages around New Zealand. So this is our comparison to the sort of global warming rate. And you can see straight away that, you know, there's warming just about everywhere around the world. And in New Zealand, we're kind of following more or less that kind of pattern, though with a lot more bumps. And on average, we're warming a little bit faster than the global average. You can see these kind of big patterns in it, though. It's not a kind of steady warming rate. So there's about 10 years, sort of around 80 to sort of 90, that it was fairly flat. And then it warmed quite quickly, and then it cooled maybe over the next decade. And then recently it's been warming very fast again. So these big patterns that we see in here are the climate signals. People might have heard of ENSO, El Nino. These big kind of climate cycles that happen around the world affect New Zealand, giving us these kind of decadal patterns. In fact, what's happening is it's been accelerating. So that warming rate has been getting faster. So if we compare the 20-year warming rates, and that's the average rate of warming over the last 20 years compared to the average rate of warming over the last 40 years, you can see that around the world, it's been going up, it's increased by about 10%. But in some parts around New Zealand, it's gone up threefold. So it's warming, it's accelerating much faster around New Zealand than it is around the world. And you can also see that what that means is that the New Zealand rate of warming is a lot faster than the global rate of warming in a lot of areas. So in some areas, especially around the coast, we're over 3 times faster than the global warming rate. So New Zealand happens to be in an area which is warming particularly fast, and the warming is kind of getting faster. So why is that happening? Well, New Zealand's at an ocean crossroads, as we've seen from Clef. And we're getting warming that's coming down, particularly from the Pacific. We're getting warming that's coming across the Tasman. They're both very strong. And we're also getting warming coming up from the Southern Ocean, not quite as strongly as from the other areas, but still warming. And because we're at this conjunction of these kind of very strong warming rates, that's why the New Zealand area is warming faster than a lot of other areas around the world. People will have seen this in the newspapers, marine heat waves. So these are generally shortish, so a month or two. Periods of very intense warming. So those kind of warming rates, 0.1 of a degree per decade, 0.15 of a degree per decade. When you get a marine heat wave, you can get areas that are 4 degrees warmer than normal. So these have really got the potential to affect biology quite significantly. And New Zealand, with that kind of average warming rate being higher than the global, we're also getting more than our fair share of marine heat waves. So this is why you get this. When you slightly heat up a bell-shaped curve like this, you get a large number more extreme events. So this kind of extreme hot end of the distribution is being pushed up by that small rise in temperature. And you can see that since 2010, the cumulative intensity, which is made up of how many marine heat waves we have, how long they last, and how hot they are, has really started to skyrocket. So we're in for more heat waves in the future as well. I always feel a bit like a weather forecaster at this kind of point. So what does this mean in terms of ocean biology? Well, one thing that's quite interesting is that New Zealand really sits on this ocean productivity bonanza. So because of where we sit in the ocean, we get this kind of particularly high primary productivity rate. So the phytoplankton are much more active, they're more abundant, and they're more vigorously growing around New Zealand than in most parts of the world, most parts of the open ocean anyway. And if you zoom in on New Zealand, you can see that we're sitting astride this kind of meeting of water. So to the north, we have this subtropical water, which is very nutrient limited, low productivity water generally. And to the south of New Zealand, we have this subantarctic water that's limited in terms of light and iron availability. And where the two meet, you get this Goldilocks zone across the subtropical front, which stretches across the Chatham Rise to the east of New Zealand and then out towards Tasmania to the west. And that subtropical front, there the conditions are just right, and you get these kind of massive blooms of phytoplankton there. And that's one reason why our richest fisheries are on the Chatham Rise, for instance. Here's a satellite image showing one of those amazing phytoplankton blooms over the Chatham Rise. And the green colour there is that kind of massive growth of this grass of the ocean, these tiny phytoplankton in the ocean, because of the perfect conditions there. And then this productivity from those phytoplankton then feed through into the small zooplankton, the crustaceans, the small fish, the big fish, the mammals and the seabirds and such like. So it all comes from the phytoplankton. So what's been happening to that ocean productivity? Well, to the north of New Zealand, it's been slight decreases, fairly static, but slight decreases. There's patches to the east of New Zealand where it's been decreasing a bit faster. To the south of New Zealand, fairly static with slight increasing trends. And over the Chatham Rise, we're actually seeing quite strong positive increases of productivity, which is a good thing for the ecosystems there. But again, it's not all straightforward. So in the subtropical waters to the north, we see this slight decrease. But then, and to the subantarctic, we see this kind of long period of kind of slight increase. But we see periods where, you know, both areas start decreasing in productivity, and then they've recovered more recently. So these reasons why you get these different patterns in productivity are not particularly well understood, which makes it hard to forecast what's going to happen in the future. So how do we do that? How do we kind of work out what's going to happen around New Zealand now? I Googled up kind of two quotes about future predictions. This is the first one that everyone will kind of know, and this is the second one. And both of these tend to be quite true for what's happening in terms of climate and ecosystems around New Zealand. It really is pretty tough to make predictions about what's going to happen into ecosystems. We're not particularly good even at the phytoplankton, so projecting that through the rest of the system is even harder. And the most reliable way, well, what happens in the future kind of depends on what we do about it. So the way that we try and project this into the future is we first have to work out what people are going to do. And we have these 5, they call them shared socioeconomic pathways, SSPs, but really they're climate change scenarios. So are we going to really go down to carbon neutral and cut down carbon emissions into the atmosphere? That's the sort of sustainability one. Are we going to do a sort of halfway job, get halfway there? Or are we going to just go full out and burn as much fossil fuel as we can? And what we do is we kind of use computer models, what we call Earth system models, to take these different options and say, how is that going to affect the ocean into the future, so that we can make some future forecasts about how much how much we can compare, how much good it's going to do against how much it's going to cost to do these different options. So this is a, hopefully this will play. It appears not. What we can do is we can take those kind of models and we can project into the future how those kind of systems are going to go. And what you find when you look at the outcomes of that is this kind of plot. So this is a plot of warming here. So this is the temperature anomaly. This is how much the temperature is likely to rise in the different months under these different scenarios. So the orange and the blue here are in 50 years and 100 years time if we take the low emission route. So these changes in temperature are about a degree. So the water will be, surface waters will be about a degree warmer than present. If we go down the medium route, this is the sort of green and red, it matters whether we're looking in 50 years or 100 years hence. So 50 years hence, we'll get away with something like 1.5 degrees. 100 years hence, it might be picking up to 2.5 degrees above normal. The purple and the brown are what happens if we're on the high emission one. And there you see at the 50-year hence, we're at about 2 degrees of warming. But what happens in 100 years time is we're up at 4 degrees in the summer. So what really matters is kind of what we do now. for 100, more than 50 years in the future. What will biology do in the future? We're not particularly good at predicting this, and it's likely to fall slightly overall, but increase in some areas around, especially to the southern areas around the subantarctic. How will this kind of move through the food web? So this is kind of some work that I look at, trying to model food webs and trying to say how that changes of primary production are going to flow through into different parts of the system. And it's quite uncertain, it must be said. So this is kind of like my best guess about what's going to happen as we get this climate change coming on in the New Zealand region over the next, say, 50 years. There's going to be movement of species. So species are going to move to try and find the conditions that they like and try and avoid the conditions that they don't like, from heat waves or from warming or from acidification, as Cliff talked about, or from changes of oxygen. The change of species and the communities is likely to change. New species are going to appear in New Zealand waters. So we're going to be able to species that haven't before managed to live in New Zealand are going to kind of move into our waters probably. Seasonality could change, so things could happen at different times of the year. There could be greater variability between years, different effects on species. So I think some species are likely to benefit from climate change, definitely. Some will lose. So there's going to be unexpected booms and collapses of different species. Condition of individuals could change. Catch limits and the way that we're doing management might not be suitable in the future. So here's some examples. So if you look at catches of fish, you see that some of the catches are going up to the south and down to the north, indicating potentially that the stock, the sort of favoured conditions, are kind of moving to the south where the water is cooler. Cold water fishes that are only down in the south are kind of not doing so well at the moment. Some of those, we're getting kind of new species arriving in New Zealand waters that we don't really know what to do with. People might have seen this around the Hauraki Gulf, some parts of the snapper stock there. The fish are looking quite emaciated. The flesh is kind of white, possibly due to starvation, due to an effect on their prey. Some species doing pretty well. I mean, you'll have seen also the boom times for snapper. That's been in the paper a lot. And indeed, and the interesting thing here, just to sort of juxtapose climate change with what we're doing in other ways on the ocean, is if you look at the stock assessment for snapper, the major stock of snapper, this is the sort of increase that's leading to that information about the boom. But if you zoom out and look at how things have changed since 1900, this is the boom that we're talking about, and this is the change that's happened due to fishing. So in conclusion, climate change is happening now. It's certainly having an effect on weather with more cyclones because the water is warmer, and more warmer waters lead to more cyclones. So things like Cyclone Gabrielle might become more common. We're seeing and we're expecting fisheries and ecosystems to change in the future because of this, and it's going to be unpredictable and unexpected things are going to happen. So what we need to manage this is we need better information, better management systems, and to respond more quickly. And I think we've got to make more use of new autonomous technology to try and get the information that we need to respond. And we've got to be aware of this sliding baseline. So what we see in ecosystems at the moment is not a particularly natural state. It's a state that's already been affected by a lot of other human activities. So we've got to manage with this whole combination of factors involved. Thanks very much for your attention. I'm looking on the chat for people that are going to be guessing, not glass eels. Very, very good guess though, but no. I'll give you another clue. It's not in the New Zealand EEZ. It's further south than that. Okay, thank you all.
Kia ora, thank you, Matt. Yes, I looked at that Jeff's comment about glass eels and I thought the eel scientists would be amazingly ecstatic if they ever saw that many glass eels hovering around off our coast. Yeah, well, I feel like you were talking about how we're trending above average and how much we're warming and the speed at which we're warming. And I know we're very competitive and we like winning, but really this is one race I'd rather we weren't trying to win. But anyway, thanks. Lots to think about. I'm sure you all out there must have some questions burning to be asked. So jump into the Q&A tab at the bottom of the screen and ask away, and then we'll get to them shortly. But before we do quick Q&A, we have a final presentation tonight from Isaac Moranga. Now, Isaac will share Te Moana, Te Taio, Te Tangata, and will reflect on cultural leadership, lived experience, and meaningful youth engagement, and how it can guide more inclusive responses to climate change. Over to you, Isaac.
Kia ora. Hopefully you can see my screen and hear me okay.
I can
Okay,
certainly hear you okay, and I can see your screen beautifully. Thank you.
Kia ora, Alison. Well, tēnā koutou katoa, ko Isaac Morunga, tōku ingoa, no Waitakere aho. Before I kick off, I wanted to first mahi to Merck, in particular Laura, for the invitation to speak and for your mahi in organising C Week in the series. I'd like to mahi to Alison for being such a gracious host, and mahi to my two amazing fellow panelists, Dr. Cliff Law and Dr. Matt Pinkerton. I do feel like a bit of a wild card in this series, so it will be quite a different pace from here on. I also want to acknowledge all those who have tuned in tonight, because your presence makes this community possible, and those listening in as well. I would also like to call out that I don't necessarily come from an academic, scientific or practitioner background in marine science or related fields like other panelists who have maybe been part of CWIC's Ngā Kōrero III Series this year, but I hope what I shared tonight might spark a reminder that you don't need to be a scientist to be a kaitiaki or guardian of our oceans and environment. There's space for all of us to contribute, to raise awareness, and to serve in our own way. I myself, I trained as a statistician, so like data and numbers is kind of my thing, but I think getting out, getting my hands dirty, being in the water, advocating for how we protect, how we show up, how I vote, that kind of stuff, that informs, I suppose, the protection of our marine environments. And I appreciate tonight's focus is firmly on OLP3, and my predecessors have unpacked this beautifully. So if we take a step back and we ask why we're gathered here, I think it's because ocean literacy calls us to something bigger, to understand how the ocean shapes our lives and how our actions shape the ocean in return. And each of us has a role to play using our voice, our hands, and our mind to care for Te Taiao. So kia ora. Go on. Tonight, I'm proud to represent not only the New Zealand National Commission for UNESCO, but also our incredible rōpū of UNESCO Aotearoa youth leaders. As youth leaders, we work to ensure young people are meaningfully engaged and empowered across the Commission's priority areas. We also serve as ambassadors and change agents, building UNESCO's profile locally and globally, and actively seek opportunities to collaborate with organisations, networks, and initiatives that align with UNESCO's values, like the Sir Peter Blake Marine Education and Rec Centre. The title of my session, Te Moana Te Taiao Te Tangata, draws inspiration from a whakatauki, or proverb that speaks deeply to our relationship with the natural world. Ko au te awa, ko te awa ko au. I am the river and the river is me. In Te Ao Māori, people are not seen as separate from nature. We are born of it. As part of the whakapapa of Te Taiao, or the natural world, we carry the responsibility of kaitiakitanga to protect the mauri, or life force of all living things, as part of our extended whānau. So we're not just surrounded by the environment, we are part of it, and that connection brings with it a responsibility to care, to protect, and to act. And if I had to summarize in one sentence what the objective of my brief session tonight would be, it is to show that climate resilience starts with people and thrives when different knowledge systems work together to protect what connects us all, which is the ocean, the land, and each other. Aotearoa New Zealand is an island nation surrounded by the moana, making us deeply influenced by oceanic systems. And when we think of the ocean, we shouldn't view it in separate parts, but as one vast, constantly moving, interconnected system. And what happens in the ocean affects the environment, and what happens on land flows back into the ocean. The ocean doesn't just respond to climate change, it shapes it. And when we look at Aotearoa New Zealand, we see this connection clearly in our weather. I mean, there were all the graphs before that were shown around the warming waters or ocean in Aotearoa. We talked about carbon. So all of that has a heavy influence on us here in New Zealand. Warm waters can intensify storms, while cooler currents may bring drought conditions. And when disasters strike, like Cyclone Gabrielle, which most severely impacted the Hawke's Bay region of New Zealand in 2023, we're reminded that tropical cyclones born over warm seas can unleash extreme rainfall and coastal damage, affecting homes, whenua or land, and communities. And not just human communities, but also marine environments, where up to 80% as an estimate of New Zealand wildlife are in the ocean. So those unseen communities as well. Changes in the ocean temperature and rainfall patterns don't just affect the environment, they reshape how we live, grow kai, sustain ourselves, our whānau, our whenua, and these shifts show up in our gardens, our rivers, our coastlines, and our communities. In New Zealand, rainfall is shaped by ocean-borne moisture, mountainous terrain, and seasonal westerly winds, and this creates a climate that ranges from the soaked west coast, beautiful soaked west coast, to the dry east. And when ocean conditions change, as we mentioned, this change is happening now, this delicate balance can tip, and we see longer droughts, heavier downpours, and more unpredictable seasons. And for many, and I'm speaking from one perspective, Māori communities, especially those living on coastal or flood-prone areas, these changes compound existing vulnerabilities, and they threaten marae, displace whānau, and disrupt cultural practices tied to the land and sea. So warmer waters can also alter fish migration routes, reduce biodiversity, and affect traditional or general fishing practices. From marakai, or traditional food gardens, to marine harvests, food systems are deeply vulnerable to ocean-driven climate shifts, and species once abundant may become scarce. Traditional harvesting times may no longer align with seasonal cues, and for communities who rely on these systems, not just for sustenance, the impact is profound. Māori knowledge system already recognize the ocean as a living ancestor. We refer a lot to Te Moana Nui a Kiwa, the great ocean of Kiwa, with rhythms that guide seasonal cycles, navigation, and well-being, all part of our histories and our storytelling. When we think of this from an OLP3 lens, how can we apply Indigenous knowledge systems to protect and respond to environmental change? Aotearoa is often seen as the gold standard for Indigenous-led kaupapa. I've had the fortune of being in many global working groups or presenting to folks from all over the world that often look at the way we marry different knowledge systems and how unique it is and how they can apply that to their own work streams. But the truth is, we've still got a long way to go. We're proud to share and learn alongside others, and we hope more countries commit to that deep ongoing work needed to truly value Indigenous knowledge and outcomes. I think weaving knowledge systems together in Aotearoa has generated a distinctive approach to how we undertake science, research, and collaboration. Embracing Indigenous and local knowledge in New Zealand includes specific perspectives, and that leads to more comprehensive, inclusive, and culturally grounded responses to global challenges. So I guess my challenge to all of you listening, tuning in either live or listening later, where it's relevant, and if it's not already part of your practice, how might you begin to weave in or meaningfully engage with alternative knowledge systems like Indigenous knowledge systems within your work, your research, or your areas of interest? Across the globe, coastal communities and island nations are at the front lines of climate change. Rising seas, intensifying storms, and disrupted seasons don't discriminate, but they do expose existing vulnerabilities. And here in Aotearoa, Māori communities do face serious risks to cultural, environmental, economic, and social well-being. Many live in flood-prone or coastal areas due to historical displacement, increasing exposure to erosion, drought, and storm surges. And impacts are not just physical, as I've mentioned before. They touch spiritual and mental well-being, as we see ourselves rooted in whakapapa or connection, and that belief that we descend from the land and sea and inherit both the responsibility to protect the land, but also the pain when the land is harmed. So what does just climate action look like? It's not all doom and gloom. There was one example that I managed to find and did a little bit of research on, and maybe there is someone in the school who knows a little bit about this work, but one example that I've found is Kotahitanga Mo Te Taiao, which is in Nelson, and I think there is someone tuning in from Nelson here tonight, which is a Māori-led alliance showing, in collaboration with the Crown, Department of Conservation specifically, showing that climate action grounded in Indigenous values can heal both ecosystems and relationships. And this partnership involves 17 iwi, councils, and DOC across the top of the South Island to work together towards a healthier environment by restoring 3.4 million hectares of land and sea into Te Taiihu, guided by Te Ao Māori, blending Mātauranga Māori and Western science. And sometimes you can marry the both as well, just different knowledge systems to regenerate ecosystems, strengthen communities, and build resilience. So there are several work streams within Kotahitanga Mo Te Taiao, but one example of a project that they did was called Wakapuaka Whangamoa Restoration Project, and that wrapped up in 2024 after 3 years of work. across different ecologically significant sites. And with guidance from Ngai Tama, the project wove tikanga into every step, from weed and pest control to wānanga on Pakakohe and Rongonga. It supported over a dozen landowners and protected habitats for species like the Marlborough mini gecko and the matata. So in 2024 alone, the project planted almost 13,000 native trees, controlled 18.2 hectares of weeds, and removed wildling pines from nearly 30 hectares. So just one example of that genuine partnership that comes out of having a different way of approaching a problem that we're all facing, which is around how do we preserve the environment and how do we protect the environment. And that's just in New Zealand. Throughout the Pacific, Indigenous communities are leading climate resilience strategies grounded in ancestral knowledge, collective action. Some of these approaches have been formally adopted into policy for some places, while others continue to inspire global movements. I mean, in Samoa and also in New Zealand, but mangrove restoration is guided by the proverb, e fofo le alamea, le alamea. Only the alamea can heal itself. So communities are using nature-based solutions to repair environmental damage, drawing on traditional wisdom to restore ecosystems. In New Zealand, I'm sure we're all familiar with this, the Wanganui River, Mount Taranaki, Te Uruwera, being granted legal personhood to recognise them not as resources, but as living ancestors. I also believe there were conversations around Māori leaders calling for whales to be granted the same status, honouring their ecological role as carbon biosinks and their deep cultural significance. In one way, it's cool, right, to know that this is something that is truly unique to New Zealand, that we have this like legal status for nature. But then on the other hand, it's kind of, in my perspective, kind of sad that we have to go through all of that work to protect nature in like this in another system, if that makes sense, without just doing it anyway. Like, why do we have to go through all these different loopholes? So just as one perspective there. And then an item I wanted to call out was starting in Vanuatu. Pacific Island law students, they led a global campaign that resulted in a landmark UN ruling stating that countries that fail to curb fossil fuel emissions may now be legally required to pay reparations to affected nations, reframing that climate justice is not just a moral issue, but a legal one. So these stories, and there are only a few stories, they remind us that climate action is not just technical, and technical has a role to play. It's so deeply important now more than ever in an age of disinformation, but it's relational, intergenerational, and deeply rooted in place. And when Indigenous knowledge leads, it also has a role to play, and resilience follows. A lot of my kaupapa, so by day I actually work in IT, and then my extracurricular role is with UNESCO and a few other things, but across the entire platform and of things that I engage with, one of the core priorities for me and other folks that I think about is how do we engage youth? Because I wonder, what is the demographic of those tuned in tonight? Often I think about youth being, well, we will be the inheritors, your children, your grandchildren, me as a somewhat young person. We will inherit the world that is left behind from our parents and my grandparents. And so there's a participatory process that young people play, the ideas, the expertise, the lived experiences that we have that should play a role in that decision-making at all levels. And how do we create outcomes that are not only effective, but are relevant and transformative for us? And I think from an Indigenous youth perspective, like how do we engage youth who might be in more vulnerable communities that honor them, their knowledge, their communities, the responsibilities they have and their identities as well. So especially when we think of, at least I speak for myself, being a custodian not only of the land of Aotearoa, but of my language, and also like the knowledge that's shared with me. So how do I share that on with others? So involving youth in research and action and projects across policy, initiative development, from design, or even just exposure. That's really, really important because all the decisions that are made will deeply and directly affect our lives moving forward and are affecting our lives today. And these are some snippets from a previous hui that we had a couple months ago around a different kaupapa, but it was around the idea that engagement is reciprocal. And so if we're serious about sustainability and highlighting the importance of a just climate transition, then youth aren't just the leaders of tomorrow, they're already leading today. And the more that we center their insights, their unique place and perspective in the world, it is so important that we honor them in our mahi. And to end off, I just wanted to say tonight, I hope is a reminder that the ocean doesn't just shape our climate, it shapes our stories, our responsibilities, and our relationships. And while the science helps us understand the patterns and the data, it's the human element that helps us to respond with the care and action. So as we leave tonight, I think all of us, we have a role to play. Ngā mihi nui, thank you. Kia ora.
Kia ora, thank you, Isaac. I should stick my hand up and confess that I'm in Te Tai Ihu. I'm in Whakatū at the top of the South Island, and Wakapuaka is just down the road from me. So yeah, it's great that there's some good work being done.
Yeah. Well, my nan lives in Nelson, so I'm also biased against Nelson, even if I am a born and bred Aucklander. So kia ora.
Confession, I was raised in Auckland too. It's not all bad. It has a wonderful gulf, although we're not doing very nice things to it. I was really struck by something you said at the beginning of your kōrero, which is we're not surrounded by the environment, we are the environment. And I think that's something that people in the middle of the city can sometimes forget. So something to hang on to. We have questions coming in. That's great. There was one more guess at Matt's mystery fish. It was Antarctic toothfish, and Matt commented in the comments, right region, wrong fish. So if you want to focus your thinking way down south, maybe someone out there has an idea of Matt's mystery fish. And a comment from Barbara in the chat, and she says, climate action includes voting, so please remember to vote if you haven't already voted. Now let's go to the questions, which Laura is managing for us. So thank you, Laura. We have a question from Michelle, which I'm not sure who'd like to answer this. Do you anticipate toxic algal blooms as are being experienced in South Australia at the moment? Because there's been a very big bloom that's been lasting a very long time over there. Would someone like to take that question?
I can have a stab at that. Yeah, I mean, toxic algal blooms are usually a combination of factors. Climate is definitely one of those. So there was definitely an occasion where there was a toxic algal bloom in the Hauraki Gulf that was caused by particularly warm water intruding into the Gulf. So unusual conditions, and warming could easily lead to kind of more toxic algal blooms. It's also linked to nutrient output from the rivers as well. So a combination of that kind of pollution plus the environmental change probably means that they are more likely, yes.
Anything from you, Cliff?
Not really that I can add to what Matt just said, because he covered all. I mean, there's a lot of still to learn about what causes these toxic algal blooms. There's a whole combination of things, and as Matt says, some of those might be driven by climate change in the future, but some of them are more local conditions that we can manage, that we can do something about. So there's plenty to learn there.
Kia ora, great. A question from Melvin, who's pretty keen on lakes, and he says lakes are smaller and they're isolated bodies of water. They often have less correlation with external factors, but even so, why are we not doing visibly active, his quotes, research on New Zealand lakes? I'm not sure it's a question to ask oceanographers, but do you think your remit should extend to lakes as well as the sea?
I can make a comment. There has been a lot of work on lakes and lake taupo. So NIWA in the day had a sort of taupo research lab that used to do a lot of work on lakes. And there's work being done on lakes, different lakes, a lot by the universities, but also by NIWA. Probably not enough. From a technical point of view, observing lakes is more difficult in some ways because they are smaller and the satellite resolution is quite challenged by looking at lakes. So, that's technological problem, and with the technology improving, we're getting finer and finer satellite data, and at some point we're going to be actually use the satellites to observe lakes. Taupo is probably the only lake that's big enough to be able to do that in New Zealand at the moment. The other lakes are pretty small, but there are different methods and different satellites where we're trying to get better observation on lakes. But yeah, I agree. More is probably needed.
I'm not sure what, we're getting a bit of interference at the moment. I think that may have actually been coming from you, Matt, which is odd because we weren't getting it before. We'll just see whether that comes back again. I did a story for Radio New Zealand a few years ago. There has been a big project on lakes called 360 Lakes, in which the Cawthron and GNS Science as was, and a whole lot of organisations collaborated together to look at various things in lakes. So look out for that. I think the 360 number was 10% of New Zealand lakes from memory. So that's something you could look out for, Melvin. A question for Cliff, I think, from Jeff. Any comments on the impact of pollution on the surface microlayer of the oceans and the relationship to climate change? Could it possibly have an effect on carbon dioxide exchange?
Well, that's a good question, and anything that affects the surface layer of the ocean is going to have an effect on climate change, because that surface layer, that real surface microlayer, as they call it, is the interface where all the gases exchange. And so anything that has an impact on it, like pollution or an increased level of organics, like an oil spill, for example, will suppress the exchange of gases and so prevent the oceans taking up CO2. But I guess take another form of example of pollution is around plastics. So plastics are something that are obviously building up in the environment, both in the terrestrial environment and the marine system, and they have a tendency to congregate on the surface layer of the ocean, where they cause all sorts of things, where they suppress the exchange and mixing. So you remember I talked about the fact that that we need the turbulence at the near surface to increase the uptake of carbon dioxide, and this plastic actually suppresses it. But worse than that, the plastic reacts under UV light and sunlight and releases greenhouse gases as well from the marine environment. So there's a number of unusual sort of secondary effects of pollution, apart from it being a terrible thing for the organisms that live there. But the way that it affects the chemistry and the gas exchange at the surface is also an issue.
Oh, another reason, as if we didn't need it, another reason for not using so much plastic.
Absolutely.
Oh, that's really interesting and also very concerning. Another question from Jeff, which is also for you, Cliff. What changes are anticipated in the ocean conveyor belt circulation, and what would the consequences be, and any idea of how soon?
That's a big question that lots and lots of people are working on. And so, of course, I didn't go into the whole thing about the slowdown of that conveyor belt. And there has been for some time a lot of concern about how that, simply because particularly things like two things are happening there, that if you're melting the ice around Antarctica and the Arctic, you're putting more fresh water on the surface, and so you're stopping this conveyor belt forming. You remember I said about how the colder water and the more salty water starts that whole conveyor belt off. Well, that will stop that. But also with the ocean's warming, it creates more stratification and less of this mixing. And so that is a concern, and there has been evidence in the kind of geological past to the Earth that things have changed there. But scientists are, particularly around the North Atlantic, they're very interested in this because the end game of the conveyor belt is the Gulf Stream. And of course, the Gulf Stream is what keeps Northern Europe, nice and warm, because it's transferring all that heat from the tropics up to around the UK and around Northern Europe. And so there is a lot of research going on that. And my understanding is at the moment, there's no evidence that it is stopping. There's been some suggestion it might be slowing down, but currently there's a lot of scientists, particularly in the Northern Hemisphere, keeping a very close eye on that in case it does actually begin to switch off, which would be quite serious particularly for the climate and the weather of the Northern Hemisphere.
Crikey. Okay. Now, something flashed across chat before, which I can't quite find again. Somebody said Antarctic silverfish, Matt. So is that the right answer yet?
Yes, that's the right answer. Well done, that one. Congratulations. If there was a prize, they'd get it. Unfortunately, there is no prize, but you can take the kudos.
What can you tell us about Antarctic silverfish?
Well, Antarctic silverfish, so they only occur over the, or mainly occur over the shelf around the Antarctic. So they're the kind of most southern in some ways of the Antarctic fish. They have antifreeze in their blood, so they're virtually impossible to freeze. Interestingly, they dominate the fish biomass down in the Ross Sea and around some parts of the Antarctic. They're a crucial prey item for penguins, seals, whales. So they're really kind of the keystone species for the Antarctic. And they haven't really got anywhere to go. So if things warm up too much down there, they haven't anywhere to go. So quite a favourite of mine, silverfish.
Oh, good luck to them. A question for you, Matt. Someone asked, what are some examples of new species coming into our waters? I know you're not a fish biologist, but any thoughts?
I'm not. I was just looking back on the example I used. Pink mau mau, maybe. That's what's in the example. But interestingly, about new species arriving, there's two parts to it. There's the environment. So the environment warming up makes it easier for some exotic species to settle here. But a big one is the pathway. So they've actually got to get transported into the New Zealand waters. So a lot of it is about those transport vectors. So things like ballast water, cleaning ship hulls, looking, the trade of exotic species. So a lot of it is actually that biosecurity.
Great. I have a question for you, Isaac, which is obviously with your work with UNESCO, you're very clued into things like the ocean and climate change. I'm just wondering, in your IT world, do you see people having much of an awareness of what's going on?
Oh, great question. In my professional life, I think there's varying degrees of understanding or willingness to understand, I think, is the key curiosity. And when I think about, even just sitting here tonight, the language that we're using, and I think for me, it's being able to connect with people through their lived experience. I think Don had a question around, how do we get more people thinking about climate change? And we use terms like ecosystems, etc. And one example I would say is like, what was their perspective? For example, if they're from Queensland, around the Gold Coast beaches suffering that catastrophic damage from the March 2025 tropical cyclone Alfred, like using examples like that grounds them on like, oh yeah, like how did that happen and where did that come from? Or is it droughts and bushfires and the frequency and the severity of these experiences? People can relate to that, or common people can relate to that a little bit more than maybe some of the approaches that I might have, or more in-depth conversations I might have with friends who know a little bit about this topic, if that makes sense. So making it accessible, coming from lived experiences, and then using language that kind of connects with them. Not assuming people are simple, just saying, if they're not engaging with the topic, how do I convince them that they should?
Indeed, it's about the power of storytelling and making it relevant. How did you get into this area, Isaac?
As a youth leader, I've been involved in different kaupapa pretty much mine since university. And one kind of key thing for me is around Indigenous, and kind of the aspiration is if we help some of our most vulnerable communities, everyone else succeeds as well. So applied for a placement on their internship or the UNESCO Aotearoa Youth Leaders Program, which if there are any youth listening tonight, we usually have applications around this time of the year, and was really lucky to get a placement 3 years ago. In my last year as the Special Advisor Youth, and we'll be going to Uzbekistan in a couple of weeks to attend the UNESCO Youth Forum. So as the only youth delegate from New Zealand, which is a real privilege. I think tonight, and also just being across a lot of the work that we're doing in New Zealand, how do we elevate that at a global platform as well? And how do I learn from other young people who are doing good work internationally as well?
Am I right in thinking you only have a 3-year term?
Correct. So this year was my last year, but I also got promoted. I don't know if I should use that word, but to the board. So sit on the board and then also run the youth leadership program.
Oh, great. So we're not losing you. That's excellent news.
Yeah, thank you.
Thank you. Now, a question, I'll just stick with you for the second Isaac. Don asks, how can we effectively convince more people that climate change is happening? But he's in Australia, and he says, I find in Australia that many people have very little knowledge of what is happening in terms such as ecosystems. So there's a sense in which you've already answered that. So it's about finding examples to make it relevant to people in their world.
Correct. Yeah, finding common ground, telling stories, and depending on their propensity to engage, that's when you might share a little bit more detail. But I think one of the biggest risks that we have in society at the moment is everyone is in their own little bubble, depending on where they're getting their information from, the validity of that information. That's quite scary to me. So what I've had to do is really think about how I convey the importance of topics like climate change, like disinformation, AI, all of that. How do I find terms and common ground to unpack that? Because yeah, it's pretty freaky out there. You know, what's out there in the world and the land of information. Yeah.
Yeah, and finding common ground is interesting. I think lots of people, if you drill down, everyone has the same hopes and aspirations for their children, for example. They want their children to live better lives, to be happy, to be fulfilled. And you do need a safe world for that to happen. So, you know, that's something that we all want and we can all aspire to. Great. Now here's a question which any of you can answer. It's from Joanna. She says, what kaimoana is the most sustainable? Are there any species we should avoid buying and catching and eating?
Forest and Bird have a really good resource on this called Best Fish Guide. I might link it in the chat. I think they have an app, but then they also released a pamphlet in 2017. I think it has been updated since then, but that would be a good place to start. And it has a ranking system of the kind of kaimoana that you should consume that are sustainable, and then obviously those that are less not. So I'll put that in the chat.
Yeah, and it'll give you some ideas of things to think about when you are buying fish, for example. Now this is a big question. What are the top 3 things, asks Joanna, that we as individuals can do to reduce our carbon footprint and show our aroha to the ocean? Who would like to start off?
Well, I can have a crack at that, because there are, you know, it's when you look at it in terms of trying to do your bit for climate change, individual responsibility is a kind of important thing. And there are things that we can do. And of course, I'm sure most people online are aware of things like just reducing your carbon footprint in terms of your travel. So whether you're going by bike, or you're getting you can get an electric vehicle if you're lucky, or you're reducing your flights or something like that, you can reduce your carbon footprint in that way. But I'm always slightly concerned about the focus that's put on the individual, because I feel, you know, there's an issue here for society that we need to move forward, because that's the only place that will make real traction here. And that where it comes down to is our leaders and our governments have to be really making the hard decisions and providing the options for how we can reduce our carbon emissions. So I think it was maybe Barbara's comment about voting. I think that's one of the things that you could do. Vote the right way if you're concerned about the climate.
Matt, what about you?
I kind of read that question, so I've been musing on that as well. So Cliff's comments are spot on. I was thinking, you know, that kind of pressure put on the individual to kind of take it all on is a bit much. So we're all, you know, a lot of us are, you know, we're kind of getting by, and that's kind of a lot. So if you can, you know, reduce your carbon footprint, that's kind of good. Another thing to add to what Cliff said, it would be look at the places that you work, and try and get the places that you work to kind of uphold good environmental standards as well. So is there some change that you can lead to within your workplace that kind of cuts down their carbon footprint? Things like that would help. But voting is a really big one too, and being aware of what's going on, trying to hold our representatives to account.
Yeah, there's a whole lot of things that you need to consider. So, you know, if I'm going to ride my bike into town, I'd like a safe cycleway to travel on. Maybe I need my workplace to give me a bicycle park. I need the local council and national government to, give us a better bus, put money into public buses, make sure those cycleways get built. It does work at a whole lot of levels, not just me getting on my bike in the morning. Isaac, what about you?
I think I think Cliff and Matt covered most of the general stuff. I think I would just come back to maybe one of my sentences I shared at the beginning, which is that each of us has a role to play using our voice, our hands, and our minds to care for Te Taiao. So whether it be voting, whether it be advocating, whether it be informing, whether it be literally going out into the moana and the beach, cleaning up, picking rubbish up, like we all have little bits add up. But again, yes, it is like broader. As a society, we have to be better at acknowledging the role that we all play. But yeah.
Yep. If I could just get into chat. Hold on a second. Let me just see if I can get in. So Barbara noted in the chat, definitely not just about what we do as individuals, but what we all do does matter, especially if we're able to. And she's put a link there to an organisation called Take the Jump, which has some simple things that we can all do without going out of our way too much. Utam says, I urge organisations to report their footprint. I work for Toy2, so partner with and use Toy2 or carbon certified products. You can do offsets if you do want to fly somewhere or you need to fly somewhere. It is possible to buy offsets. You could go and volunteer and plant some trees. I do that sometimes. There's all sorts of benefits from doing that. Thanks, Joanna. She says, what a privilege to have such knowledgeable and awe-inspiring presenters and to have access to all of your wisdom in this free format. It's great, isn't it? We learn heaps. So I think we've burnt through everyone's questions. So I've got a comment, which is the International Day of Climate Action is coming up later this month on the 24th. So that's something we could all get involved in. And even if that climate action is just having a chat to someone on the bus or someone you're sitting next to in a cafe, just have a little conversation, say hi. Is there anything else, Matt, Cliff, or Isaac, that you would like to comment on before I bring it? Oh, Barbara says, I have a question unanswered about CO2 removal. Beg your pardon, Barbara. There is an outstanding question. It's probably for Cliff. Mechanical carbon dioxide removal sometimes gets attention as a way to reverse climate change. What do our panelists think about this? Start with you, Cliff.
Yep, that is something that's on the agenda at the moment and is becoming more common. There's, we talked about the emissions reduction, but there's a recognition generally that if we're to meet the kind of goals of being net zero by 2050, so the Paris Agreement, that it's not, even if we reduce our emissions, we're not going to achieve those goals without actually actively removing carbon dioxide from the atmosphere. So that means kind of mechanisms on land or potentially in the ocean where we can accelerate the removal of CO2. So, there's these things called they call them artificial trees, where they're actually stripping CO2 out of the air. So mechanical systems pumping air through chemical traps where they're removing CO2. And on the other side of things, trees are basically that. So kind of what we're doing through our forestry in New Zealand is part of our climate strategy to artificially increase the removal on the land of carbon. But the oceans is fast being considered now as an option. If you think about, going back to what I was telling you in my talk, is the ocean has a lot of potential in terms of what they call these natural solutions. So if you can enhance some of those removal processes, you might be able to get the ocean to take out more CO2. Now, the government has, in its recent emissions reduction plan that was released at the end of last year, for the first time, they've identified the marine system as a potential option for removing carbon through mechanisms like blue carbon systems. So by blue carbon systems, I'm talking about things like mangroves and seaweeds and salt marshes. So restoring and growing more of these. But they're also talking about potentially about larger schemes which increase the uptake of the ocean by stimulating the phytoplankton to grow by adding nutrients. Now, there's clearly issues here. the ocean's in a bad enough way without us tinkering with it. But on the other hand, if the solution is there, the potential is certainly there. But is it the solution? Who's to say? There's a lot of research that's got to be done to understand, whether this is a right or a wrong move here. And so it's interesting with the government's drive to actually identify that. There's going to be a lot more, I think, taking place in this to consider the risks and the co-benefits, the opportunities and the other things that need to be put in place if we're to consider the ocean as a solution to the climate problem.
There's something from Jeff in the Q&A as well. Comment on the impact of zinc on phytoplankton populations. Does zinc increase algae growth?
I can probably take that one. Zinc does affect some sorts of phytoplanktons in very small amounts. So certain groups might benefit from the addition of zinc in the ocean, or there being more zinc available to them. What the main thing, it goes back to my last comment I just made about phytoplankton growing, is that the thing that they're actually lacking a lot of in the ocean is iron. A lot in our waters, and particularly all the waters to the south, going all the way down to the Antarctica, the phytoplankton are very low in iron, and that's why people have talked about the potential of adding iron to the ocean to get the phytoplankton to grow and remove more carbon dioxide.
So many things that are possible, but no obvious silver bullet. Well, I think that might do it. I have learned huge amounts tonight. So thank you, Cliff. Thank you, Matt. Thank you, Isaac. Thank you so much for sharing your wisdom and your knowledge and sharing your time with us. Thank you to you, our audience, for joining us in the final webinar of this series. I'm a bit sad that it's the last one for this year. Kia ora, and many thanks to Laura from Seaweek, who's been working away behind the scenes to make all this happen. A big shout out to you. Thanks, Laura. You, our audience, if you can take a moment to please fill out our survey, which we're posting in the chat, and we'll also send out a follow-up email that will have this link too, because we would love to hear what you thought. So this brings us nearly to the end of our Ngā Kōrero III series, with just 2 ocean literacy principles left to explore, which we will be doing next year. So we're not leaving them undone. Sea Week 2026 will be in March. There will be events all across Aotearoa under the theme of Ocean Literacy Principle number 6, that the ocean and humans are inextricably interconnected. So check out the Sea Week website, follow us on social media, join the mailing list to find out more, and do get involved in events in your area. If you are in Auckland, the final in-person event for the series will align with the International Day for Biological Diversity, which is May 2026. We'll be looking at principle number 5, that the ocean supports a great diversity of life and ecosystems. Don't forget, if you missed our previous webinars, they are all online. You can find them on the Sea Week website. Look in the news tab there. It's also on Sea Week's YouTube channel. Now, in closing, nō reira, ngā mihi nui a koutou, tēnā koutou, tēnā tātou katoa. Thank you very much for joining us. Remember, toi moana, toi tangata, healthy seas, healthy people. Thanks for your company. Thanks for your awareness and your good work for the climate. Hata marie, po marie, good night.